Our speaker today is Nolen Scaife. He just tutored me on how to pronounce his last name, which of course is unbelievably complicated, and I apologize to him. However, he's still interested in the University of Colorado Boulder, and so I didn't mess up too much. So, designing robust defenses for modern payment systems. This involves technology, cybersecurity, and policy. All of those things are in play, and Nolen is going to give us a sense of what some of the critical issues are with technology, cybersecurity, and policy for payment systems. Please, everyone, welcome Nolen Scaife.
Thank you. All right, thank you very much. I am Nolen Scaife. I'm from the University of Florida. Thank you for coming to my talk today. And I want to start by talking to you about a maxim that comes up repeatedly in payments, and that's Suttons Law. Now, Willie Sutton was a famous bank robber in the early 1900s, and when he was caught, he was famously asked why he decided to rob banks, to which he said, because that's where the money is. And of course, during this time, if your bank was robbed, your money was gone. It was literally where your money was. And there were two major changes at the time to help curb bank robberies. The first was that the federal government will insure your deposits, so if your bank is robbed, you can get your money back. And the second was that bank robbery became a federal crime, which allowed organizations like the FBI to go after people like Willie Sutton. Now, these were innovative ideas at the time, and in fact, this problem was largely thought to be solved by the end of World War II. But as people came back from war and banks had additional money, robberies went back up. And in fact, it wasn't even until the late 1960s that mandatory security measures were even made for banks, like safes and security cameras. But it turns out that requiring a camera in a safe doesn't solve the problem of bank robberies, just like requiring crypto means that your data is safe. And so having a great idea doesn't necessarily fix the problem. Now, in academia, we have the luxury of being able to think about these problems and design elegant solutions, but having a great technology and getting it deployed is another story, because our solutions don't necessarily solve why the existing solution is still deployed. Now, overcoming that's really hard. I mean, take a look at IPv6 or SBGP, where adoption is still a really hard problem. So I want to take you back to where the money is today. And today the money is in your wallet. Now, card fraud continues to rise year over year, and it's estimated to cross over $30 billion next year. And this is notable because for the last few years we've been deploying new technologies to help solve this problem. And I'm going to walk you through how these attacks work. But as I'm going to show you today, protecting deployed payment infrastructure can be done accurately and inexpensively. Now, payments are fundamentally an embedded systems problem. And what I study are their interoperation, their software, their hardware, and how users interact with them. And this requires a multidisciplinary approach that spans hardware security, software security, reverse engineering, signal processing, and many others. And I've published in top venues for many of these, and I hope you'll see that this kind of approach is necessary for solving these tough problems. But today I'm only talking about my work in payments. So I'm going to give you some background first. Now, this is Magnetic Stripe's 50th birthday this year. This technology is 50 years old, and it's completely plain text. It contains all of your bank account data, the account number, your name, and so forth on the magnetic stripe. You can simply read it off and copy it. And you may be familiar with the CVV2 value that's printed on the back of your credit card. You're typically asked to provide this when you do some sort of online transaction. But what you might, and it's designed to prove that you have possession of the physical card. But you may not know that there's a CVV1 value that's actually on the magnetic stripe, and it's designed to ensure that you have the complete magnetic stripe data. So for example, you can't take the account number off of the front of the card and make a magnetic stripe and have that work. You have to have this CVV1 value. And so what that means is that cloned cards are easiest to create from the data obtained by reading the card, which we're going to see a little bit later. Now, card cloning is an expensive problem with a lot of losses, so banks have started to deploy chip cards. And EMV tries to make card cloning more difficult. This is the protocol that your chip uses to communicate with the terminal in the bank. Now, you've all seen this. And I'm sure you've all been told that this fixes the problem, but you've all been to a store, I'm sure, that looks like it should take the chip, and it doesn't. And in fact, even when the chips fail, what do? You use the magnetic stripe. In fact, most terminals here in the US, if you take the chip and you kind of plug it in and unplug it in quick succession 3 times, it'll say, please just swipe, and it'll take it. And even if you use the chip, it's trivial to make a device, interestingly, that can just query your card data off of the chip, and then you can use that to make a magnetic stripe clone. And we're going to talk more about this throughout the talk, but Murdoch et al. Said in their kind of seminal paper on this work, chip and pin is broken, and chip and pin is broken. In fact, this is what one of those might look like. You might see this at a restaurant or at a coffee shop. Please don't use the chip. And so, how do criminals get this data? Now, this is primarily done with card skimmers. And the goal of a card skimmer is simple. Copy enough data to make a financial transaction. There's not a lot of specific information about skimmers that's out there, and we couldn't hope to tackle this problem without measuring it. So we partnered with the NYPD, who gave us data about skimmers that they had recovered over a 16-month period. And we found 35 unique skimmers out of several hundred that they found in New York. Now keep in mind, NYPD employs 4 full-time detectives that do nothing but card fraud because this is such a large problem there. So out of these 35 skimmers that we found, we taxonomized them into these 5 types. And the first are overlay skimmers. You may have seen something that looks like this before. This is a fully independent embedded system that's designed to fit over the card terminal, such that when you put your card in, this device gets to read your card, and the ATM or the payment terminal that you're using also gets to read your card. If you flip these over, and I will show you a picture of that later, these have batteries on the back of them. They have storage equipment. So they're fully embedded, they're fully independent systems. And the second kind is very similar to this, these deep insert skimmers. Deep insert skimmers are fundamentally the same as overlay skimmers, but instead of putting them on the outside of the payment terminal, they actually cut these so that they fit into the free space that exists inside the payment, inside the card acceptor, and then they slide them in with a special tool like a credit card and push them down. So that it exists inside the terminal and you can't see it. But you can see these have batteries. You can see the battery actually up there. And it has independent reading hardware as well. The third type are EMV Shimmers. I mentioned to you before that you can simply query the chip on your card and ask it for your card number, your name, and the expiration date. And the chip will happily provide that to you. And of course, criminals know that, so they're making these devices to acquire that data. It's actually printed on a flexible piece of circuit board, and they stick it into the chip slot so that when you put your chip into the slot, this device performs what we call a man-in-the-middle attack on your card. It first queries the data, stores it, and then allows your transaction to go through. Next, we have Wiretap Skimmers. You might think of this as being, if there's an ATM that's plugged into a wall, they'll come by, they'll unplug it from the wall, plug it into the skimmer, plug the skimmer back into the wall. So it sits kind of in line between the payment terminal and whatever its next communication hop is. We're not going to talk much about these today because these indicate some sort of other fundamental vulnerability, that they're not using crypto or the crypto is easily broken, for example. And finally, internal gas pump skimmers. These are man-in-the-middle attacks that happen between gas pump card readers like this one. There's a ribbon cable that attaches this to the inside of the gas pump. They simply disconnect it, plug in this device, and then plug it all back up together. And it captures the card data. We're going to talk a lot about those. And by the way, these are all deliberate. If you can't tell, these are all deliberately designed to look, feel, and act like a regular payment terminal to make you feel safe so that you'll use it. And they're all malicious embedded systems too. So if you're thinking though that I have a PIN on my card, on my ATM card, and they're not going to get my PIN, and so my data is safe, well, think again. Criminals use devices like PIN pad overlays and cameras to capture you entering your PIN so that they have both your PIN and your card data. You can see this pin pad overlay. It actually sits on top of the pin pad so that when you press, when you're pressing the buttons on this pin pad, it actually presses through into the ATM and it captures the pin. And this one was actually, despite the fact that it was brand new, the detectives told us that they could tell that it was brand new because it was not dirty on the flip side of it. It's been deliberately designed to look worn to make you feel less suspicious about it. And the cameras, what they'll do, for example, this is over here on the right, this is an ATM light fixture. So, if you've ever been to an ATM that has lights that shine down on it so that, you can kind of see it and see the surroundings, they actually steal those light fixtures, drill small holes into them, install the cameras in them, and then take them back and put them back in so that they can capture your pin. And in fact, this is a 1 millimeter hole. I've circled it in red. But what we found was that detectives, when they go out looking for skimmers, they actually look for the signs of the camera because the camera is easier to spot than the skimmer in most cases. Now you may be wondering how people don't get caught installing these. This is real footage from a real skimmer. Someone has this in their pocket and they're walking into it's like a convenience store that has a small ATM, and they take it out, they stick it on, and then they're done. And they actually sit there. If you keep watching the video, they look like they're interacting with the ATM so that they look like a customer so that people don't get suspicious. But these kinds of overlay skimmers are actually affixed so tightly to these that the criminals have to come in and pry them back off with a knife. You might have been given advice, for example, to make sure you grab and wiggle on a payment, a card acceptor before you use it in case it's got a skimmer on it, it'll come off. They actually use really strong adhesives, or they're designed with such tight tolerances that they actually clip to the unit so that they have to be forcibly removed. Okay, so first today we're going to look at a major use case I'm sure a lot of you are familiar with in the room, gas pumps, and look at the tools that are available to consumers to detect skimming. And then we're going to look at how one of the most common types of skimmers works and how these can be better detected. And finally, we know we're not going to catch all of them. So I'll talk about how criminals clone cards and how these are different than legitimate cards. But first, let's look at gas pumps, where new technologies have historically had a hard time being deployed. I doubt any of you have ever used the chip on your card at a gas station. Most of the time, you just dip it in and out quickly. I haven't ever used the chip on mine. And Visa and MasterCard understand this, and that's why they keep extending the deadline for requiring EMV deployment. But the reason may surprise you. It turns out that it costs $6,000 to $10,000 per pump to replace the payment terminal hardware in a gas station. Now, there's hundreds of millions of dollars of fraud in this area, but that averages out by store to only about $700 in fraud. And what does that mean? That means that if you're a small business with 6 gas pumps, it could take you your entire lifetime to recoup the cost of deploying EMV hardware. So it's no wonder that this market doesn't want to deploy this. And so take a brief aside here to talk about the problem of attacking gas pumps in the first place. Now these are themselves embedded systems, and securing them spans problems in many different areas. You can see them up there, but the attacks are very simple. What they do is they'll rent a U-Haul or a box truck. They'll pull it up to the gas station to block the view of anybody who's trying to see what they're doing. They take a small set of master keys, they have a ring of these, and they open the pump, they install the skimmer, and they close it. Well, what's wrong? Most gas stations don't change the locks first, so most of the locks on gas stations are actually either bad or they're one of a few sets of master keys that ship with the units. In fact, the locks on these are so bad, we were out with a detective looking at gas pumps, and he took his file cabinet key from his office and opened a gas pump with it. So they're really bad locks. And there's no alarms. The terminals don't disable when they're opened. It's just a free-for-all, really. And we know that there's no real financial incentive to solve this problem, so you might wonder if gas stations even care about it. Well, it turns out they do care. And gas pump upgrades are really costly, so merchants have started to use these kinds of security seals. And they're intended to make the customer aware of if the pump has been opened. And I want you to note how it instructs the consumer to report a problem. And merchants implicitly ask us to perform this check for every transaction. Now, we've beaten browser security interfaces to death, and arguably we've made this better. And this is effectively an embedded systems security interface. But unlike browser interfaces where there's only 3 or 4 major players and we can look and we can inspect the effectiveness of these seals come in hundreds of sizes, colors, and brands. And furthermore, research shows that these seals are easily defeated, especially in voting security. But we wanted to know if they were effective in this domain. Now, there's a lot of things that have to go right for a consumer to evaluate a seal. You have to know if a seal should even be present. Is it placed correctly? What's its purpose? You might look at this photo and think this thing is being taped together by these, that it's falling apart and this is some sort of makeshift repair. You also need to know if it's the correct seal. For example, this is an Exxon pump with Exxon seal. I know it's hard to read, but it's got Exxon seals on it. But in Orlando, for example, the municipality actually provides Orlando branded seals for gas stations to use. So, if you go to an Exxon in Orlando, it might have this sticker, it might have the Orlando sticker on it. And finally, if all of those things are right, you have to be able to tell if the seal is indicating tampering. And it's not really clear that consumers are equipped to evaluate these seals. So we looked for some data to see if these work in practice. And so we worked with the Florida Department of Agriculture and Consumer Services, who records data about skimmers at gas pumps. In Florida, this organization is solely responsible for gas pumps. They're the law enforcement agency that's responsible for these. And so just in case you can see, these are the reports. There were a little over 2,000 reports, and we mapped these out. And as you can see, this follows the major highways and interstates in Florida. And the Department of Agriculture, what they do is they go out, they open the pumps, and they inspect them for skimmers. And they can do that legally. They can force gas station operators to open them. They can't decline that. And so what this makes is over this period, this is the most comprehensive data set available for skimming attacks in the entire world. And it contains open response fields on the state of the pumps when skimmers are found, which can tell us a lot about what security measures are present, if any. And so we took these open response fields and we had 2 researchers code these fields for thematic analysis. There were about 1,200 records were annotated. We found 30 unique themes. Our Cohen's kappa for this was 0.94, which corresponds to almost perfect agreement between the two researchers. In fact, before I flip to the next slide, I want to show you that this seal actually is installed on the hinge. So this door opens this way so that the seal won't break when it's opened. Okay. So it turns out that over an order of magnitude more pumps have intact, correctly placed seals than any other problem, including broken or incorrectly placed tape. And our law enforcement contacts tell us that there are 2 main reasons for this. First, attackers simply replace the seals after they install the skimmer. They open it up, they break the seal, they put a new one on. Or employees fail to check for skimmers before reapplying a seal. And in fact, we were out looking for skimmers with the Department of Agriculture, and we saw a pump that had no seal. All the other pumps at the station had a seal. This one didn't. So we went inside. We said, "Hey, look, pump 3 has no seal on it." And the person that was working there reached under the counter, pulled out a roll of seals, went out, put one on it, went back in, put the roll of seals back, and went back to work. So that really does happen. So what's wrong? Seals require consistent placement and visuals, and this is a classic time of check to time of use vulnerability. The seal should be placed immediately after inspection, but these results suggest either that inspection fails or the seal is placed after the skimmer is installed. And in fact, this particular seal, you can buy it online directly from the company that makes it for only $69 for 500, and then you can apply them wherever you want. So, but what about technical detection methods? These clearly aren't working. So what about technical detection methods? So We got all of the apps from both Android and iOS's app stores that were marketed to detect skimmers. And this might be, this is a reasonable approach because some skimmers have a Bluetooth data retrieval capabilities. I'm going to talk about that in a second. But we got these apps, we decompiled and analyzed the code for all of these to try and find the detection mechanisms that are used by the apps. Now, Android apps, of course, are more straightforward to analyze. I don't know if any of you have done that. But Dalvik bytecode and Xamarin C# apps decompile really well into readable source, like the Skim Plus app you can see in the corner of the slide. But iOS apps are actually a lot more difficult. We had to jailbreak a device to decrypt the app, and then we had to have a second iOS device to do live debugging on it, which made it even more difficult to do. Now, before I show you these apps, I want to describe why this seems like a reasonable approach. Now, if attackers don't have to come back for the device, it's far less likely they'll be caught. Now, on the ones that I showed you that were ATM overlay skimmers, they have batteries on them. They only last a couple of days, and criminals have to come back and pick up the skimmers so that they can recharge them and get the data off of them. In fact, that's what police officers do when they find one, is they just leave it on there, wait for somebody to come pick it up, and arrest the person that picks it up. But in the case of gas pump skimmers, where these are powered by the pump, if they don't have to come back, then that's a lot less risky for them. But if you look at the Bluetooth stack, there's actually only a few places that you could detect this. You know, you could say, is a Bluetooth device present? Does it have a particular MAC address? Does it have a special name or a special PIN? And so forth. But you know, at a gas station, there's a lot of Bluetooth happening at gas stations. You know, my car, my watch, my phone, your car, your watch, your phone, everybody's car, everybody's watch, everybody's phone, plus whatever else you have that might also have Bluetooth. So let's look at how these apps actually work. So Skimmer Scanner represents over 100,000 downloads in particular. And this is how it works. It scans Bluetooth devices in range. If it finds something that's named HC-05, it tries to pair with it using 1, 2, 3, 4 as the pin. It creates a serial socket. It sends 1 byte. If the byte it gets back matches, it says, aha, I found a skimmer. The next app was very nice. They actually changed the name, so if it's HC-05 or HC-06 and everything else is the same, it will detect it. Now, Skim Plus is actually really interesting. So Skim Plus alerts if any Bluetooth device's MAC address begins with one of these prefixes. And these prefixes, if you're not aware, these 3-byte prefixes are called OUIs, organizationally unique identifiers. They're assigned to a company that makes network devices to identify the device to the manufacturer. They're assigned by the IEEE. And so, you know, we expect to see 3-byte prefixes for some of these. But what was interesting to us were these 2-byte prefixes, this 2016 and this 2017. It turns out that these were actually, because they're not complete OUIs, they should be assigned to multiple manufacturers probably. And it turns out that that's kind of the case and kind of not the case. 2016 was assigned to Intel and Lite-On and a number of other companies you've heard of, and 2017 had absolutely no assignments, which indicates that some module manufacturer is selecting non-standard MAC addressing for their devices. But ultimately, what we can take away from this is that, you know, trying to detect skimmers via these OUIs is going to cause some false positives because there's going to be a lot of collisions. Certainly not all of the devices that have these 3-byte prefixes are skimmers. Although maybe a large percentage of them are when compared with, or you know, when in the range of someone who's using the app. Okay, so the next app, I'll show you an example. So this is the code from it. This code actually starts when the app has a button that says Scan for Skimmers. You press the button, it starts here. This is what it does. The first thing it does is it shows you an ad. In case you wanted to buy something right now, you can see the ad. The second thing is it shows you a list of Bluetooth serial devices that are in range. It enumerates these and puts them into a list for you, which is nice. And then it always says no skimmers found. So This is an app that uses Apache Cordova, by the way, so this is all kind of JavaScript. But unfortunately, the grammar is not the worst part of this app. It actually just always tells you that no skimmers were found. And it turns out that this is the case kind of across the board for the rest of the apps. The other apps can't detect skimmers. 2 of the Android apps just show you an ad and tell you no skimmers were found. One iOS app tries to crowdsource the locations of skimmers but doesn't return any data. And the second iOS app alerts on any Bluetooth low energy device with a long name. Now, we've never seen a skimmer that uses Bluetooth low energy. And I've seen a lot of skimmers. But it turns out that iOS doesn't actually allow apps to scan for Bluetooth classic devices, which are what most of these are. So it's not even possible to develop an iOS app that can detect skimmers, or that detects the skimmers we've seen at least. So these detection mechanisms seem brittle, but how do they stand up to real skimmers? So we obtained 6 internal skimmers from law enforcement from their evidence. And then we characterized these and we evaluated whether or not the apps would detect these. We would power the skimmer on in the presence of, use one of the apps in the presence of one of these skimmers while it's powered on and evaluate whether it would work. It turns out that 3 apps detected 2 skimmers. And the other skimmers weren't detected because either they use a Bluetooth interface that's not supported, it's not in a blacklist, or they don't use Bluetooth at all. In fact, one of the skimmers required USB they'd have to come back, plug something up to it to get the data off of it. And the other one, and it's turned out that this is actually increasing in prevalence, uses cellular. So it has a GSM module in it, it's got a SIM card, and as soon as you swipe your card, it just texts your data to somebody else and they can do whatever they want with it. But it also turns out that the skimmers that were detected were configurable. We got the development documentation for these modules, and it turns out that they're configurable using serial interface, using what are called AT commands. And I'm sure, if you're not familiar with those, they're just kind of old school commands that you could use to issue to a modem to do certain kinds of tasks. One of the tasks you can do on these is you can change the name and the password. So we put them in configuration mode, we changed the name and the PIN, and we retested each app with a modified skimmer. Now, we knew from the code analysis what to expect, obviously, but this allowed us to confirm our findings. And frankly, it was easier to reconfigure these than we expected, and it was well within the range of an attacker's capabilities. And so then there was one app. Skim Plus detects 2 of those 6 skimmers, regardless of the configuration. But of course, it does so by matching the MAC address on the modules. And so, if you're an attacker and you want to evade such a system, what could you do? You could not use Bluetooth. You could use a different module. You could spoof the MAC address. And it turns out 2 of these are already happening. So should we abandon all hope? I mean, asking consumers to check for these, the available information at the gas pump to the consumer is really insufficient for the consumer to determine if there's a skimmer present. The seals and notices are inconsistent, hard to read, and require attention. Internal skimmers, they're easily installed, and there's no universal wireless trace for you to pick up to kind of build a universal detector. So what should we do? Well, the first thing we should do is change the locks so that they're not driving around with keys or file cabinet keys that can open these. But we can also take a lesson from the development of strong pin pads like what you would see at a grocery store, supermarket around here. Many of these have dead man switches in the plastic so that if you open them, it actually destroys the device. Obviously, you wouldn't want to destroy a gas pump, but the idea is kind of the same, that once the device is open, it has to be inspected to be put back into service. And if we have to use the seals, we know from research in our community, especially about browser security warnings, that the best way to get the user to be aware of a potential problem is to interrupt their workflow and have them, explicitly say, yes, I see this seal, yes, it has this correct serial number on it, or so forth. And so what do all of these do? They force attackers to use external skimmers. If they can't get into the payment terminal, like in an ATM where security controls are stronger, they're going to go back to using external type skimmers, either the ones that fit on the outside, the overlays, or the ones that fit in the payment slot. And one final note, this work's being used by Florida lawmakers actually to make changes to the Florida law to require better locks instead of security seals. Go figure. So, okay, I've shown you how gas pumps rely heavily on these tamper-evident seals that aren't working and the technological measures that also don't work. So next I want to talk about how we can make a better skimmer detector. So, after looking at the NYPD data set and inspecting a wide variety of card readers and skimmers, we decided to look more closely at overlay and deep insert skimmers, because these represent the majority of devices. Over 3/4 of the skimmers that are found in New York City are overlay and deep insert skimmers. And of course, if we can make stronger controls at gas pumps, we can force attackers to use these devices. And there are 3 properties that are common to these: touch, surface material, and size. Now, fundamentally, read heads are transducers. So when the head passes over a card, a voltage is created from these changing magnetic fields. And this voltage is the signal that you can decode. I'll show you a picture of that later. The magnetic field strength on these cards diminishes at an inverse cube rate to distance. And so at this rate, the signal becomes completely unreadable just microns away from the surface of the head. And keep in mind, these fields are already really weak. It's not like you can take a credit card out of your pocket and stick it to your refrigerator and it'll stick. And it's very weak fields. So every device we looked at has a mechanism for pushing the card onto the head or the head onto the card. And reader manufacturers, legitimate ones, part sellers, skimmer manufacturers themselves in their instruction manuals say you have to touch the head to the card or you're not going to be able to read it. Now, in order for the read head to function, the head has to be a conductor in at least those positions that align with the card data. And that's because for it to produce a strong signal, we have to produce a lot of voltage, relatively a lot of voltage to read it. So constructing the track aligned sections of the read head out of metal provides this low resistance and maximizes the voltage induced by the magnetic stripe. So due to this, the face of the read head has to be a conductor. And finally, to keep skimmers small, adversaries need the smallest magnetic read heads they can get. In fact, you can go onto some of these sites and you can buy really small read heads that are only, a millimeter or 2 deep. And they're $800 to $1,000 for just this part. But every head we looked at, including these kinds of heads, they all make 1.5 millimeters of contact over the card, and that's because it's about 1.5 millimeters wide, the data track that's on the magnetic stripe. So anyway, we looked at sites that sell these skimmers, and they sell similar heads, and they all still make exactly 1.5 millimeters of contact. Okay, so in the end, they're small, they're metal, and they touch the card. And a picture is worth 1,000 words. So this is the back of a real skimmer. In fact, this is the skimmer that I showed you the video of it being installed earlier. You can see the camera up here. This is a pinhole camera that took that video. But I want to draw your attention to the circle here in red. You can see the head. Well, it's kind of hard to see actually. You can see the head. There's a spring here that pushes the card onto the head. And this is exactly 1.5 millimeters of electrically conductive material. Okay. So it turns out that the most common way to pull this attack off is to add an additional read head, such that when a card is inserted, both the skimmer and the original read head both get a chance to read the card independently. And so using these fundamental properties, our hypothesis was that we could count the number of read heads that touch the card and alert someone if it's an abnormal number of them. And so we tried a number of designs, but by far the most successful design that we had for this has traces, electrical traces, positioned on a card where the ISO standard data tracks are, and you can see those there on the right, such that when a read head passes over this, it completes a circuit. Now, the head actually is curved, interestingly. The head's curved and it makes only a very small amount of contact with the card at any one time. It took us almost a year to get to this design iteration. But this is what it looks like when you measure that. Now, this is a dip reader, so you put the card in, it's just like this. You put the card in, and you take it back out. So your card actually passes over the read head twice, once when you put the card in, once when you take it out. And so when you instrument a card reader with a skimmer, you can see it simply doubles the number of contacts that it makes. And so by counting these spikes, we can effectively count the number of read heads that have touched the card. And so once we were sure that we had gotten this right and it worked in kind of our sandbox skimmers, we developed an enclosed prototype and had the PCBs professionally printed. We call it the Skim Reaper, and I have one here. And I would love to show it to you. So after the talk, if you want to come up and I'll demo it for you, you can see it. But effectively, it's this card. It has the traces on it, like I said. And the way it works is it applies a voltage on one half of it. It bridges over the read head when it touches it. And then this device counts them and alerts you. So we flew out to New York City to test this with detectives. And they gave us access to 10 skimmers we had never seen. 8 overlay skimmers, 2 deep insert skimmers, and we were able to do 5 swipes on each of these and had a 100% success rate. Detected the read heads in these every time. And interestingly, after we did this, we rode around with detectives in Manhattan in an unmarked police van looking for skimmers. That was where the name Skim Reaper came up. But we didn't find any while we were out with them that day, but since we've left them, they have, I believe, 7 of these devices in their possession. They've since found a skimmer with it, and they're using it in ongoing criminal prosecution of the person that installed it. So it works. Now, if you've ever had a card wear out, you might have put tape on the stripe or seen somebody that's put tape on their stripe or actually put their card in a plastic bag to try and reduce the amount of noise that's present when they swipe it. You know, this is a common thing I used to see a lot. And so we were curious if you could just put tape on a magnetic read head, a really thin non-conductive tape on the read head to make it non-conductive, which would potentially evade detection. And so we got a really thin non-conductive tape and we put it on a real skimmer and then tried to read a card with it. We actually gave up after trying to read it 50 times, because the signal quality was so poor. And it turns out that the reason for this is that the heads that are on these skimmers are very, very small. And you could probably fit 5 to 10 of them in the size of a read head that you'd see at a Walmart or a Target. It turns out that they're so small, they're not actually very sensitive. And so while this trick works at a grocery store, it actually attenuates the signal too much for these small skimmer heads. Okay, so now we talked about the fundamental properties of these skimmers and how we can use Skimmer's own technology against them. We developed the Skim Reaper, and we made a startup to produce and distribute these to law enforcement agencies. So next I want to talk to you about what happens with skim data. You know, we know we're not going to catch all of the skimmers with the Skim Reaper. And if you remember at the beginning of the talk, I mentioned that skim mag stripes are most useful for making cloned cards. And that's true. And the hardware used to do this cloning is called a card encoder. We bought 3 card encoders from 3 different manufacturers blind. And we were really surprised when they came in and they all looked pretty similar. And in fact, the software that comes bundled with them is also pretty similar. And then we took them apart to look at them to see if they're functionally identical. And not only are they functionally identical, the manufacturer from one of them was printed on the circuit board of another one. So, and there are tons of other encoders that are out there. But getting them is not quite as easy as you might think. A lot of the vendors that we called actually requested identity verification, and they wanted to know what we were going to do with them, and then we told them, and they told us, no, you can't have one to do that. Well, frankly, I wouldn't have sold us one either, knowing what we were going to do with it. But if you're going to fly under the radar, these are the kinds of card encoders that you're getting. And so you might wonder, does this really happen? Of course, criminals use gift cards to launder and steal money and to pay each other because it's semi-anonymous. They even encode card information that they acquire on the internet. They emboss them with names and they take them into stores, rubber banded together in a bundle, and they try cards until they work. And in fact, if you think this encoder looks familiar, it's because I just showed you 3 that look exactly like it. So to better understand how we can detect these counterfeit cards, I want to talk to you first about how the cards are encoded. Magnetic stripe cards are encoded using double frequency encoding, and it uses magnetic flux transitions to mark data points. The easiest way to think about this is if you had bar magnets and you just kept arranging them, back and forth, north and south alternating. But when you drag this across a magnetic read head, it creates this signal. Now, interestingly, double frequency encoding encodes a clock, a regular signal, as part of this signal. So when you're reading it, you expect to see some peak with regularity. And the clock signal is why when you go to the store, you can swipe the card slow, you can swipe the card fast, it doesn't matter. The terminal can still synchronize with the data because the clock is actually present on the card. And in fact, the clock signal in this scheme is actually just the zeros. So you can see, you have this peak with regularity, and then if there's a peak kind of mid-binary here, then you would call that a 1, otherwise it's a 0. You actually, after you get to looking at this for a while, you can just read it from pictures, which is a little weird. Okay, so the ISO standards allow some variance in the positioning of these, because it's not really possible to always get it 100% right. And that variance is called jitter, which will be important momentarily. Now, when your bank or a retailer decides to make cards, they actually load cards into a hopper and they send them down a manufacturing line at a relatively consistent speed. And they use what are called linear optical encoders to really measure the position of the card in this manufacturing line. Because this clock signal, you need to apply it with some regularity. That's the point of it. But that also means that you need to know where, in relation to the card, in relation to the head, where the card is at all times. And in this scheme, this works by keeping track of that using expensive encoding equipment. However, when you use a manual encoder and you swipe it through, you're actually accelerating in the track. And these have really cheap rubber wheels in them that spin to kind of let it know when where the card is in the track. But you get there's some negative effects with that. You get slippage in the track. The encoder itself is low resolution. You also have these kind of fundamental control system problems. So you have this latency between where it measures the card and when it can actually take an action against the new data that it's receiving. The hypothesis here is simple. Does the difference between these encoding methods influence the data encoding on the card? Both of these methods actually produce cards that conform to the ISO standard, but as we'll see, their outputs are actually wildly different. So it turns out our physics department is home to one of the only quantitative magnetic microscopes in the world. It works by using a layer of film called magneto-optical imaging film, which bends light in the presence of magnetic fields. The upshot of that is that you can look down into the microscope and you can see how magnets work. So they have this microscope. And it takes about 4 hours to image a credit card. It only takes really small pictures and you have to move it across to continue taking photos. But what you get out of this is that each image that comes out of it, every pixel in it is exactly 2.08 microns. So you can take these images and you can measure magnetic fields with them. And so this is what that looks like. When we measure the clock signal on remember when I said you could just, these are zeros and this is a 1, you can just read the pictures. We took a credit card and we cloned it, and we aligned it onto this 1 here. And what I want you to notice is the consistency in this jitter, the consistency in these bit widths actually, between the original and the counterfeit. And the counterfeit is obviously far less consistent with the placement of these. And in fact, you can kind of see this more easily if you just look at the left and right of the image. You can see that the counterfeit card's data arrives early and exits the photo late over the same space. Now, if you zoom out and you do this over the whole card, you can see that this clearly validates the hypothesis. There's definitely a difference between these two cards. Well, obviously, no one wants to wait in line for 4 hours, while we pull out this big expensive microscope and we scan your card and we try to decide if this is legitimate. By then, your milk is spoiled and your frozen goods are all melted. So we wanted to see if we could do this with commodity hardware. So we built a card reader and software to actually take the raw waveforms of these as you swipe the card and try to measure them. And to do that, we developed this measure called Jitter Variance. And it's pretty simple. We just calculate the difference in samples between these clock peaks, and then the difference between those, which gives us the jitter. And then we discard the first 10% of that array and measure the variance over the remaining values. Sorry. And the reason why we discard the first 10% is simple. We did a number of experiments that show that the most acceleration that occurs when you're at 0 and you're swiping the card through occur in the first 10% of it touching the read head. And so that unduly influences the variance because you're much slower at the beginning of the swipe than you are throughout the rest of it. So getting rid of that actually resolves that problem with no loss of ability to detect. So this jitter variance value provides a single value measurement of how consistent the jitter is for the card, such that cards with high jitter variance are less likely to be produced in a controlled facility like the one that I showed you before. So to evaluate this, we worked with Walmart, and they gave us 650 brand new gift and stored value cards. We checked them, they didn't actually have any value, but they gave us these cards. We swiped and recorded each of these cards 10 times, then we cloned those and swiped each of those 10 times. So it was about 13,000 swipes and some very sore arms. But this is what we got out of it. Now, for those of you who aren't familiar with ROC curves, this type of graph shows the true positive rate on the y-axis and the false positive rate on the x-axis for a range of threshold values. Now, we want to be in the upper left-hand corner for maximum accuracy, which you can see we are. And for our detector, the threshold was the jitter variance value, which we said all cards above this value are counterfeits and all below are originals. And that upper left corner in the ROC corresponds to the optimal threshold, which you can see in the density plot here. But you can clearly see that there's two distributions here. But if pictures don't sway you, we also did a two-group independent means t-test. This is a null hypothesis test where our null hypothesis was that there's no statistical difference between the jitter on the originals and the copies. As you can see, we had a really large effect size, very low p-value, which allowed us to reject the null hypothesis and confirm that these are statistically significant. But this is just gift cards. How does it fare on credit and debit cards? Now, as you can imagine, getting credit and debit cards is much more difficult than getting gift cards for a number of reasons. But we were able to get 55 brave people to give us their credit and debit cards, knowing full well what we were going to do with them. And we cloned those and performed the same experiment. And credit and debit cards still perform very well. But you can imagine that the quality of these cards is actually a lot less than brand new gift cards. These were cards that were bent, that were peeling, that were cracked, the kind of card that you might find in your own wallet after 3 or 4 years. And so what happened was, as these cards age, they get some noise on them. That noise makes it hard to do peak detection on the signal, and therefore, gives us some challenges in making an accurate detector. So we tried the noise here is non-deterministic, it turns out. So we tried a majority voting system. We'd swipe each card 3 times and then just return, best 2 out of 3, essentially. And that actually increases, you can see that in the ROC curve, that actually increases the accuracy of that to gift cards. And we performed, the same t-test here with similar results. So, if you're like me and you're sitting out in the audience, you're thinking, aha, I have this idea. I'm going to build a motorized reader that defeats the system by making the most accurate, cheap motorized reader. And we know that there are high-end encoders that can write consistent jitter. I mean, obviously, this is what your bank uses. So if you're willing to invest bank levels of money, you can produce cards that look like a bank made them. But we were curious if, how other kinds of lower cost motorized readers would fare. And it actually turns out we tried 2. One at a $250 price point, one at an $8,000 price point. The $8,000 one is actually the unit that our university uses to make ID cards. It turns out these are actually worse than hand swiping, and the reason for that is the control system speeds up and slows down the card as it's pulling it across the read head. It's trying to maintain a consistent speed, but in doing so, fails miserably. And so actually the cards that come out of these are actually worse than a fast hand swipe. Okay. So skimming was thought to be solved, you know, the EMV solves this problem of card skimming, but it doesn't. And it turns out that the big reason it's not is that magnetic stripes are entrenched. You know, we have legacy hardware, we have business challenges, consumer behaviors all play a part in this problem. And believing that some magic solution is going to come along and solve these is ridiculous. You know, just because, for example, you throw crypto at a problem doesn't mean it'll solve the problem, let alone be deployed. So I hope I've convinced you today that deployment is hard. We have to work together in our community to solve these tough problems. And we started by talking about how gas pumps rely on tamper-evident seals for their security, and how these and other detection methods fail. Industries kind of hoped that consumers could figure this out for themselves, but that hasn't worked in other areas of CS, and it hasn't worked here. Next, I talked about how criminals acquire this card data and how we built the Skim Reaper. Again, please come up here and see one after the talk. To detect overlay and deep insert skimmers by trying to detect multiple read heads. And finally, I talked about how we won't catch them all. So we talked about we examined how criminals create counterfeit cards with this data and how we can detect fake cards by measuring what we call jitter variance on a card as it's swiped. Now, unlike other methods, ours can be checked. Our system is deployable with only software. It doesn't require hardware changes to major terminals in order to generate this data. So what's next? Today we've been talking about people, cards, and terminals, but this is only a small piece of this ecosystem. And it turns out that it's also made up of not only instruments and terminals, but gateways, payment processors, payment networks, and issuing banks that make up the authorization process. And settlement networks and acquiring banks that make up the settlement process. And so, you know, on frontline systems, I'm interested in the detection of chip-based skimmers, terminal security analysis, and newer payment protocols like EMV contactless and EMV QR. And deeper into the system, I'm interested in looking at how these networks fail to authenticate various features of cards. You know, I told you that you can simply query an EMV chip, and it'll give you the account data, and you can use that to make a magnetic stripe. But if you go and you read the protocol, which I don't recommend, it's something like 800 pages for EMV, that actually should not work. And it turns out that the reason it does work is that in this pipeline of vendors and hardware that authenticate authenticate transactions, someone doesn't. And of course, when that happens, that opens the door for fraud. So smart criminals aren't taking guns into banks anymore and robbing them. They're actually attacking electronic systems like this. Because like I said at the beginning of the talk, or Willie Sutton said really, that's where the money is. So you might be thinking, this is cool, but what can we take away? So I work to identify the fundamental actions that adversaries have to take to be successful, and design defenses that target these actions. And sussing out which actions are fundamental to attacks is hard, but it's necessary for building robust detectors like you've seen today. And so by applying this methodology, my work has not only produced the counterfeit card detector and Skim Reaper that you've seen today, but also one of the most successful ransomware detectors on the market. And so today I've been talking, like I said, about my work in payments, but my work has spanned a number of other areas you can see here. And these are all important on their own, and they're highly relevant in payments. And my work is informed by my industry experience to develop inexpensive, elegant solutions for common problems and help them get out into the real world. And with that, I'd like to take any questions.
You've already thanked our speaker, and I'm fantastically pleased. Thank you, Nolen. It was wonderful.
Thank you.
All of the students who are registered in the T-Learn class, can I see you in the back of the room, please? Thank you. And so please proceed. Lots of questions, excitement, etc. And oh, by the way, I will never use my credit card at a gas pump ever again. So
that's right. We're all walking now. We're all walking.
So,
yes.
You described some fairly fairly high-end technology that goes into it, making a skimmer and deploying it.
Yeah.
Who are the adversaries? You have a sense of adversary empathy
Yeah,
and so
yeah. So when we were working with the NYPD, they said essentially this is all done by organized crime. And essentially in New York, there are two kind of crime organizations that do this. They don't like each other, and so they try to keep their technology out of the other group's hands. But essentially, this is made up of a hierarchy. The people who install the skimmers don't typically know much about the operation, right? You might think, for example, an ATM has a camera on it. We'll just go after the person who installed it. But oftentimes the person who installed the skimmer on the ATM was here only briefly or paid just a little bit of money, flown in and then flown out, and so folks don't know them. The people who actually make the skimmers, who are highly trained electrical and computer engineers that build these and professionally print these circuit boards, are actually right under the boss. So most of the manufacturing and distribution, they don't know who designs them. They just receive a package and they go install them, and they know where to send the data when it goes. Now, an interesting anecdote here is that the NYPD was telling us about a bust. You might think, well, how do they get their hands on these ATMs to be able to, build these really complicated shapes and injection molded things that make us feel safe using an ATM that might have a skimmer on it? And it turns out that they have insiders at the companies that manufacture these, at the parts distributors. They did a raid of a warehouse and found that there was a whole wall that was lined wall to wall with ATMs that had been purchased or stolen from various places. They had the equipment to manufacture the skimmers on site, so they had people that were doing soldering, they had people that were making circuit boards, they had people that were doing the plastic molding, all on site, and it was just, it's a business for them. Yes, sir.
In the diagram, or in the example where the read head had a thin film over it,
Yeah.
the signal attenuation. So does that indicate that if I was to put that thin film on my stripe, that would be a reasonable anti-deterrent? So or deterrent, so in other words, you were assuming about it being put on the head so that they could defeat your detector. Could I put it on my card to defeat their reader? Yeah,
potentially, but not for all types of skimmers. So potentially if you were to go to a place that you expected might have a deep insert or an overlay, certainly we think that would not be successful for the attacker. It also, though, runs the risk of, for example, getting stuck in the ATM. If it was an ATM that feeds the card in. But in the case of gas pump skimmers, where it's actually skimmed outside of that read head magnetic stripe interaction, then it doesn't help, because if it can read it, then they're just going to pick it up on the line. Yes, sir.
How quickly are the criminals using the cards after they've been captured?
So that depends. ATMs are usually pretty quick, from what I understand. They'll say that they collect the data, they very quickly make a set of counterfeit cards, and then what NYPD told us was the case was that they'll go up to someone random on the street and say, we'll give you $1,000 if you take this stack of cards to that ATM and purchase, or and just take out money until it won't let you on each card. And then they give the person $1,000 because they're reputable, and they take the rest of the money and leave. In the case of skimming with, say, credit cards and so forth at gas pumps, they can hold on to those for months before they use them. And part of that is to kind of deter where they're targeting with skimmers. As a consumer, we like to associate our card being skimmed with the last place we used our card, but that's actually pretty rare. Usually they hang on to the data for a little while before they use it. And in fact, many times they just take the data and they put it up for sale. I don't like to use the term the dark web, but they put these up for sale on sites that are hosted on Tor and other anonymity networks. And you can go and, for $5, I can buy one credit card. So if I have, $100, I can buy even more. And they will, these criminal organizations, these websites are actually designed to have a good customer service experience for you. So they'll oftentimes offer to perform a test transaction for you before you purchase it. So you say, I want 20 cards, and they'll say, do you want me to test them? Yes, and then they'll do 50-cent transaction or $1 transaction on a card, and then only give you the ones that it worked on. Or if you buy a card and it doesn't work, you can go back and say, hey, you sold me a bum card, and they'll say, okay, we'll give you a refund, or here's another one. I mean, they're in the business to try to be legitimate to the people who are doing this.
So that would lead into the next question. So how much is statistics being used to quickly detect the criminals so they can figure out where the skimmers are present? So are the credit card companies being able to say, okay, we know it's 7-Eleven at this cross street because we can show that this many cards have been used fraudulently, so we know where to map out where the criminals have been.
So they do this in some sense. For example, Visa does this, and some banks do this, where if they've got a large number of fraudulent transactions, they'll cluster them together by transaction location. So they'll take me and you and 10 other people's cards, and they'll say, do these people have any merchants in common? Where there might be a skimmer. And certainly that is where, for example, one of the law enforcement agencies that we work with went out and found a gas pump skimmer that had been there almost a year because they got a call from a bank that said, hey, you may have a skimmer at this location. I think the challenge is not in necessarily finding them like that, although that can help them get the skimmer hardware back. The problem is that those the fraudulent transactions that have been done with that have already been used to buy something, resell it, launder, etc. So the money is gone. It's just a matter of finding the hardware at that point. Yes, Dan.
So I have a question about the incentives back when you were talking about the cost to upgrade the gas pump to the chip reader, right? It seems even worse than that because the loss due to the skimming doesn't come back to the gas station, right? I mean, there's no, or is there?
Well, it does in some sense, right? Merchants aren't always absolved of the fraud that's committed against them. So in the case of actually, here's a great example. So one of the types of cards that's really popular to get skimmed at gas stations are gas cards, right? You think of Gainesville Police Department in Gainesville. They have fleet cards that they use to fill up their cruisers, right? And when these get skimmed, they're used almost immediately to buy $1,000 worth of gas in Miami or Orlando or somewhere far away, right? Why that doesn't get caught from a fraud standpoint, I'm not sure, but they sell the gas, right? And what criminals will do is they'll take minivans or pickup trucks, they put waterbed liners in them, they fill them with gasoline, so they buy hundreds of gallons of gas with these stolen cards. So at that point, to the merchant, the gas is gone, right? The gas is totally gone. They've lost that gas. And then what the criminals do is they drive to truck stops. They sell diesel for pennies on the dollar to truckers who, in many cases, truckers have to buy their own gas out of their own pocket. It comes out of their profits. So if they can buy gas for less money, then they make more money. And so it's an interesting criminal enterprise, I guess. Sir.
I have a question about so a comment made by somebody traveling to China is, there are no credit cards anymore, everything's done by phone for that. So I don't know exactly how long that will take to occur in the United States, but is that a remedy to the card problem, is just be done with cards?
I'm not sure. I think here in the U.S., where this is primarily self-regulated by Visa, MasterCard, and the payment card industry, that they, not only would they have to decide that they want to, switch to only smartphone payments, but here, absent any legislation that forces merchants to do this, merchants are going to stick with whatever works and is low cost for them. An interesting case study, I think, would be if you remember when pay at the pump came out in the US, it happened, it seemed like it happened overnight. And gas stations that did not deploy pay at the pump closed their doors. And it turns out pay at the pump cost about the same as it cost to deploy EMV. The difference is that there was no consumer. And with EMV, consumers don't demand this. And so they don't demand it. Merchants don't have any reason to do it. And I think if we want to go to something like smartphones or whatever the next thing is, it's going to be groundswell from consumer support that drives that from the merchant angle. Yes, sir.
But consumers don't really care. I mean,
Yeah.
We're going to get our gasoline, we're going to keep driving our cars. I mean, what's the motivation for consumers?
Well, for credit and debit cards, you're correct. There is none. I mean, here in the U.S., you know that we are largely absolved from the impact of financial transactions, right? You can call your bank and they'll give you the money back. But that's not necessarily the case in other types of payment systems. If you look at, I can't think of any of the names of them, Venmo and some of these other organizations that kind of fly under the regulation of being a bank, you don't necessarily have the same consumer protections in those cases. And so I think it differs depending on how you get your card data stolen or how you get a fraudulent transaction as to how you're going to react. Yes?
Have you considered changing teams? I mean, given everything you know.
You know, it's so funny.
Are you looking for partners in that?
One might say that the criminals are so good at doing this that they might make more money in a legitimate business, you know, of manufacturing devices, and you know, they could make card terminals, for example. And certainly, there's a lot of money to be had here. Yeah. No, I haven't considered that. For the record, I'm looking at the camera.
So again, let's thank our speaker.
Thank you.